Okay, we'll talk about the discovery of the CMB radiation. The cosmic microwave background has an interesting history, and so we can talk about uh, well, actually, the observation and discovery of the CMB radiation was one of the great scientific events of the modern era. It made the Big Bang cosmology much more credible, as it's difficult to see how else such a thermal radiation over this cosmic scale could have been produced. So we can talk about discovery and its interpretations. George Gamow and his collaborator Alpha and Herman first predict in the late 1940s that a direct consequence of the Big Bang model is the presence of a background of relic radiation with a temperature a few degrees. However, their contribution was not widely appreciated, and no effort was mounted to detect such a micro background. In fact, for a lot of people, it could be forgotten. Not until 1964, Bob Dickey at Princeton University rediscovered this result and led a research group to set up to detect it. And the group made of Peeble and Rowe and Wilkinson. Uh, some of the people in the books are big players in cosmology for many years. While they were constructing the apparatus, the legend goes, Dickey got a phone call from Arnold Penzias and Robert Wilson of nearby Bell Lab, Princeton, New Jersey, and the Bell Labs, New Jersey, only not many miles apart from each other. And the story goes that Wilson and Penzias told them what they had measured, and the young collaborator were in the same room, and Dickey turned around, said to them, "Boys, we are scooped." Penzias and Wilson had used a horn-shaped microwave antenna to do astronomical observations. And this is, in fact, called the Tiki Radiometer. It just shows uh, how the dominant figure Tiki was in the radar. Uh, After the Second War, all these people invented radars, and so this particular one is, in fact, is a Tiki Radiometer. And it was originally used for satellite communication experiment by the Bell Lab. And it was then, for whatever reason, not used it to given to Penzias Wilson to use for astrophysical research. And it was known to have some excess noises. But Penzias Wilson were not content to ignore it and made a careful measurements of this background radiation and find it to be independent direction, time of the day, or the season of the year. While puzzling over the cause of such a radiation, they were informed by one of their colleagues of Princeton Group's interest in the detection of a cosmic background radiation. In fact, people, as young postdoc, have given a colloquium on the subject in another university, I believe, Johns Hopkins, and so the academic grapevine passed eventually. So Penzias was heard about it. So they made the phone call to Princeton. This resulted in the simultaneous publication of two papers, one in which Penzias and Wilson announced their discovery, the other by the Princeton group explained the cosmological significance of the discovery. Because microwave absorption by water molecules in the atmosphere, it is desirable to carry the CMB measurement at locations having low humidity or high altitude. Thus, some of the subsequent observations were made with balloon-borne instruments launched in, for example, in Antarctica, because low temperature, low humidity, and high altitude. Or even better, above atmosphere and satellite. And this was accomplished in the early 1990s. Of course, it took more than 10 years to build a satellite by the Cosmic Background Explorer Satellite Observatory, COBE satellite, led by John Mather and George Smoot, obtained results showing that the CMB radiation followed a perfect blackbody spectrum with a temperature of 2.725 Kelvin. And so this is uh, the measurement results, and it's measured against frequency, and this is the intensity. Okay, the spectrum is measured by the FIRAS instrument on board COBE, and the horizontal axis is frequency because it's 1 over wavelength in centimeters. The vertical axis is power per unit area, per unit frequency, per unit solid angles. Okay. In order to make the error bar visible, this estimated uncertainty has been multiplied factor 4. In other words, the measurement fits the experiment so well that the error bar is less than the thickness of the line draw the theoretical curve. So what they did is they multiplied by a factor 400 in order to see these error bars. And also, COBE satellite the first discovered called the temperature anisotropy. It was in every direction you look, you have a blackbody spectrum with temperature 2.725. But this is not exact perfect homogeneous because on the fourth decimal places on micro Kelvin levels, there are variations. So that's the anisotropy we're talking about, which we'll see will contain a lot of cosmological informations. Now we'll compare the photon and baryon numbers. Okay. Remember, knowing the radiation temperature, we can calculate the number density. The number density relates to the cube of the temperature with known coefficient. So if you plug in the known temperature, you translate this into 410 per cubic centimeters. So it was now in the universe, on average, the 410 photons per for every cubic centimeter volume. This to be compared to the baryon number density, which is calculated in the previous lecture, which is the number of baryon or number of protons is about 0.23 per cubic meter. Okay, so therefore, you take the ratio of the baryon to photon numbers, come out to be 6 × 10⁻10. So it was for every proton or neutron, there are almost 2 billion photons. This also explains why the average energy at the decoupling time, the photon energy is 0.7 electron volt, is so low compared to the hydrogen ionization energy, 13.6 electron volt. You would think, once you follow the 13.6, the ionization will stop. The reason because there's such a high density of photons that even though the average photon energy is 0.7 electron volt, there's still enough photon in the tail end of the distribution, the high enough energy to ionize the hydrogen. So therefore, it can hold off the transition to a much lower energy than naive would expect. So that's the end of this second part of lecture 26.